I will essentially be dealing with the notion of vector fields today. So let's start. So probably in the morning you already saw some things. So this I will in some ways follow the book of Thorpe, which I understand is the book that you are prescribed perhaps, or which you follow fairly closely, so that it's easier to. So in some places I will deviate a little bit. I'll say a few things extra, but by and large I will, especially with notation and so on, I'll stick to what is in thought. So we can go in a cohesive fashion to towards understanding what we actually want to understand. So the crucial idea behind vector fields is that it can be used very effectively, because surfaces for us, as you would have seen in the morning, uh, are what one calls regular surfaces. Yeah, so you have these are level sets of certain functions whose gradient vector field is non-vanishing. Yeah, so these are hypersurfaces in Rn plus 1. So that will be typically our case. And so it's particularly effective there to study the geometry there. So it's a tool to understand geometry. You will see this as, so both in my lectures and the other one. So that this is a pervasive tool to use everywhere, especially useful because we are looking at level sets. Yeah, so that is, and one may also add that this is of independent interest in differential topology. So which is just topology, where you study topology using methods of calculus. So those 2 points I want to mention. And so let's see. So I will start setting up notation. So this will take us a fair while. Some of this probably is going to be a repetition, but so repeating some things does no harm to anyone. So a vector v. So my vectors will always have little arrows on top, just to distinguish them from scalars. So a vector at a point in Rn plus 1 is a pair. So it's a point together with an element of Rn plus 1. So the viewpoint here is that we view V as somehow being attached to the point P. So how do we think of this? So we think of this as the usual vector from, when you say a vector in Euclidean spaces, what do you think? It's always an arrow which starts at 0 and ends at your given vector, right? So uh, instead of that, what we will do is it's merely translated, so that parallelly translated, so that it starts at P and just move so that the starting point is P. Yeah? So the direction is still the direction given by the original V. Yeah? So that's the pictorial point. So maybe I write this so in brackets. So think of V, the vector V, that is, as the translate, and this is the crucial bit. Maybe parallel you can write. So because the direction is still given by the element V in Rn plus 1. Uh, so as the translate of the usual vector starting at 0, I write that without the arrow just to make a distinction at 0, so that the tail is in P. So it starts at P. So pictorially, maybe it's sometimes useful to draw pictures in these things. So let's see. So y-axis, x-axis. So this is the origin. So x, y. So your original vector is something like this. So we join origin with that. Let's say, so this is v. Then what you do is simply, p is some point here. Okay, so now the tricky part in drawing pictures is to draw them correctly. So hopefully this will look like it is parallel. Not quite. Maybe should tilt a little more, but okay, I'll leave it at that. So it looks slightly longer as well. So let me see if I can do that correctly. But otherwise, you understand what I. Okay, so this is P comma V. Yeah. You can think in terms of Cartesian coordinates. Yeah. So we, let's say in R2 given by a pair xy, and so what should translate the coordinates of the translate be, so that we denote this by p comma v, the pair. So that will be a vector for us. So this will always have an arrow on top, just to make this clear. The important point of such vectors for us is that it has a vector space structure. This is a crucial bit. So maybe I write vector space once. I'll usually abbreviate to VSP. So on the set, and I will call this the tangent space to Rn plus 1. So therefore the notation T for tangent at the point P. So what is this by definition? This is the set of all vectors V which start at P, and V is arbitrary, as an arbitrary element of Rn plus 1. So I call this, without comment, I call this the tangent space of Rn plus 1 at P. So the vector space structure on this is, so okay, so what is the set, of course, of, maybe I write it in words as well, of all vectors starting at P, at a point P. The set, on the set, maybe I write set here, of all vectors at a point P. P itself, of course, is a point in Rn plus 1. So how is this vector space structure given? So this is given by, so there's a natural vector space structure on Rn plus 1. This essentially inherits that. How? So what is addition here? So you add two vectors. So you want to end up with another vector which lies in TP Rn plus 1 itself. So, okay, so what is V? It's a pair P comma V. What is the vector W? It's a pair P comma W. So you define the addition to be P comma V plus W. So you keep the point fixed. So it's simply looking at all possible vectors which start from P. That's it. Yeah? So, as V varies over all directions and lengths, in fact. So you can, this is the vector addition. So what is scalar multiplication? In order to have a vector space structure, you need that. So scalar multiplication, again, you do it only in the second coordinate. So that's the, so this is alpha PV. You have to say what the action is on this pair, and that I define to be P comma alpha V. So this gives the vector space structure. So in particular, this vector space structure tells us that if you start with a basis for Rn plus 1, then you get an associated basis for the tangent space at P, for any point P in R. So you look at all pairs now, where the second coordinate is just the basis vectors that you started out with. So that's how vector addition here is defined, right? So this is a basis for the tangent space P at Rn plus 1. So you can in fact look at as a set at least. So as a set, we can consider the set of all vectors at all points together. It's very useful to do this. So in this case, it's rather trivial, but the idea itself is very useful. So the set TR n plus 1, without reference to a point in the subscript, uh, of all vectors, maybe I should just write it in words. So maybe okay, it's okay to write it in words. So set of all vectors at all the points. Yeah. So at all points P in Rn plus 1, you can consider them together. And this is, of course, just, Rn plus 1 times Rn plus 1. Right. So there are two. So this is all pairs P comma V, where P varies over Rn plus 1 and V varies over Rn plus 1. So this is just, in fact, equal to. Yeah, so there's no. And so this, just to give some fancy names here, it's called the tangent bundle. So you just put together all the tangent spaces together. And in this case, it's sort of the trivial one. So I'll sort of put trivial in bracket, so for reasons which we won't go into. But I just want to impress upon you that it is very useful to consider all tangent spaces at all points together as one object. So in this case, you see this, you can, so Rn plus 1 is a very nice, as nice as a space as you can get. Perhaps one thing, so if you're starting with these things, is to remember you can never add vectors at different points. That's to be remembered. So that's the vector space structure, is that you can only add vectors. So when you specify a vector, you specify a point P and all sorts of directions based there. So it's a trivial remark, but perhaps if you're seeing such things for the first time, it's a useful one. Because explicitly, you see, when I write vector V, I'm not writing a subscript P just because it is cumbersome. So that's why I understand when I say a vector V, it already means a pair. There is a point which I'm specifying and an associated element of Rn plus 1 that I'm specifying. So, okay. So, of course, on Rn plus 1, there is a natural inner product. Yeah. So the dot product, which we know. And because the vector space structure respects this vector space structure of Rn plus 1, you imagine that the inner product structure on Rn plus 1 is also carried over to the tangent space. And this is a crucial idea again. So this is where, in some ways, as we will see, geometry really begins. Yeah? So because what you want to do in geometry, you want to be able to measure, unlike in topology, you want to be able to measure lengths of curves, angles between various curves. What is a triangle in this space? So you want to be able to measure angles and lengths. And so that means that you want, as we will see, what we actually want is an inner product on the tangent space at every point. So as we will see, this is how it will turn out. So for now, we'll just define this. we can expect this, as I said, because the vector space structure is really on TP Rn plus 1 is really carrying over the vector space structure on Rn plus 1 itself. So we simply define the inner product between two vectors v and w to be the usual dot product or the standard inner product. So this is for all v is equal to p comma v, and w vector w is p comma w in tprn plus 1. Right? So this, where on the right hand side you have the standard inner product, the dot product. So this is the standard dot product on Rn plus 1. So, okay. I'll mention in passing, of course, that you can define a cross product as well on TP of R3. So we won't say anything about it immediately. So I just mentioned it orally at the moment. So, of course, once you have an inner product, we have an associated norm, and so we can therefore start measuring angles and lengths. Right? So that is, we can do geometry. So this means that we can actually go to do some geometry over here. So associated to this, we have a norm. So maybe I write can measure lengths and angles. That is, we can do some geometry. So that's what distinguishes geometry from topology, for instance. Yeah? So, okay. So what is the norm of a vector v? So we think of this as the length of the vector. Yeah. So this is simply the inner product between v and v square root. Of course, from standard dot product, you know that the inner product of a vector with itself is non-negative. So if the vector is 0, it is 0. Otherwise, it's actually strictly positive. So you can take its unique positive square root. Yeah. So the right-hand side is a well-defined real number. So called the length of the vector v. So in linear algebra, you have studied inner products, right? So I'm somehow, otherwise, okay, we only care about the standard dot product because everything sits inside Rn plus 1. But it helps if you have seen this before in slightly more general contexts. So occasionally, of course, you have to help me out by saying what you know or what you may not know, because otherwise I perhaps repeat something which you know while passing over something which you do not. So this we call the length of the vector v. Then, of course, you also have the angle between these vectors, right? So once you have an inner product, so in this case, it's just the standard dot product here. So the angle between two vectors the vector v and the angle theta between vector v and vector w is given by the relation that cosine of theta is the inner product of these vectors normalized to length 1. So maybe I write them together. So length of v. So you can consider the associated unit vectors. Yeah. So divide v by the length of v, w by the length of w, and so this, of course, theta lies between 0 and pi. Okay, so that is, I think, all we might need to start with, at least, in order to say what a vector field is. So, what a vector field does is it associates to points in some open subset of Rn plus 1 vectors at that point. Yeah. So we'll write this formally down, but that's all it does. So you can actually view it as a map from a given space to its tangent bundle. So that's a point of view that we could actually take with great profit in great generality. So that's what we will do here as well. Already, when we go to surfaces, we will see that we need a little more information because of the Euclidean space. This is all going to be very nice and easy. So what is a vector field? So it's a function um, which we again denote now by capital letters, but with an arrow on top, from u to actually Rn plus 1 cross Rn plus 1. So recall that the tangent bundle was this product. So if you specify a point P in the first coordinate Rn plus 1, then you have TP of Rn plus 1. Yeah? So where U, of course, is something sitting inside Rn plus 1 itself, typically open, right? I'm not going to insist on this, but let's say it is open. So unless otherwise mentioned, this is going to be open. Yeah. Um, so what does it do? Is a function which assigns to each point P in U So notice that P is actually sitting inside Rn plus 1. So it's a point in Rn plus 1. But not every point in Rn plus 1 we are going to look at. A vector in the tangent bundle, in the tangent space at P. Yeah. So vector in TP Rn plus 1. That is, so your vector field X is a function. So, say is a map, if you wish. So function maybe for real valued and maps for vector valued. So what does it do for at a point P? It gives you a vector at P. How does a vector at P look like? It is P, and notation is XP would be the associated vector that we will look at. So where now X itself you can view as a function, where so X, so where is this from? So P is fixed, so it's a map from U to Rn plus 1. So we'll look at examples of vector fields. And perhaps maybe I make a remark that because of the way we define vector fields here, what we can do is we can actually have a 1-1 correspondence between vector fields X with arrow on top and functions, maps X from U to Rn plus 1, right? So what I will do is, so notice this. So vector fields on U, so is a correspondence. You can think of these as the same objects. Maps from U to Rn plus 1 is a map. So therefore, so in examples, I'll still emphasize that the function X, maybe I write X here, maybe, yeah, so it's vector field X on U corresponds to a function map X from U to Rn plus 1. So that arrow, so vector fields have an arrow on top. So in all these examples that we will see, I will make a distinction between the two, but you can, for all practical purposes, think of a vector field on an open subset of Rn plus 1 as being the function. So, but for drawing pictures and so on, this is nicer to actually follow the definition closely, and just for practice of understanding what the definition is as well. So the first example we will see is a constant vector field. It's the easiest thing you can think of. So what should this be? So this is maybe just on R2. So this we can do in any dimension, but maybe a lot of the examples will be here in R2, because some of them we can actually visualize very nicely, and it's helpful to draw pictures in this context. Okay, so constant vector field, what should it do? So first of all, it's a map from R2 itself. U is my R2, I take all of it, and to R2 to R2, right? So recall that a vector field here was a map from, on an open subset U of Rn plus 1, was a map from U to Rn plus 1 times Rn plus 1. So here n is 1. So you have a map from R2 to R2 times R2. So how is it defined? So defined by P is actually P and any fixed point that you can think of in R2. So this is a vector. No? So this is for every P in R2. So it's a constant. So what is constant here? That is the associated function x from R2 to R2 is constant. Is the constant function, constant map, v going to, I mean p going to 1 comma 0 for every p. So x of p, the function is constant here for all p. So so maybe the exercise here is, so things write in black are typically things you should think about. So, okay, so the second one then. So what is next? The next easiest thing after a constant is just the identity map. So so the identity vector field. So so what will this do? So you already see, what should be identity? The function associated to the vector field should be identity, should be the identity map. So I'll again, because these are the first times we are seeing these things, or at least that I'm mentioning them to you, I'll write both what is the vector field and the function separately. So again on R2, is, so how is it defined? So defined by the vector field at a point will give me a tangent vector at P. But what is the tangent vector that I'm going to do? It's going to be the point P itself. This is for every P. So that is the associated map X is the identity map on R2. Again, the exercise for you is to draw a picture. Okay, so let's look at third example. So example 3. So I'll call this something. So okay, maybe I should say the name as well. So we'll see a little bit later why it's called this. So rotation vector field. So again on R2, and I define this by, so now I write it in a shorter form. So this is xy, comma, minus yx. So what does the, so already maybe if you think of this in terms of maybe complex numbers, so x comma y, the pair x comma y being x plus iy, maybe you can see why this is called the rotation, right? So because what do you do? So from x plus iy, how do you get minus y, x minus iy? Yeah, so sort of, or so y minus y plus ix, so to speak. So it's multiplication by rotation by pi by 2. Yeah. So, but okay, so we will. So what is the associated function? Maybe I should write it here as well. That is x of x comma y. So p I've written in the usual Cartesian coordinates here. Of course, you should just fix a couple of points, x comma y, see what it does, and you can actually see this very well. So what I did, of course, is one of the points advantages of doing these offline is actually take pictures from the book and put it here. So I'll just copy this. So if I was doing this in person, perhaps the only thing would be you would have worse pictures. So if I try to draw these things, it would never be as well good. Okay, so the exercise is actually solved for you in the text, and so I simply give you the picture. Yeah? So maybe I should have draw a picture and then given this to you. Fine. Now, okay, so since vector fields are maps between suitable spaces, so we can talk about continuous vector fields, smooth vector fields, etc. And we say that a vector field is continuous or smooth. These are the two things we'll sort of concern ourselves with. If the associated function is a continuous or smooth. So call a vector field, maybe I write the word, so call a vector field x. Let me fix this. So u to Rn plus 1. So u is always open, right? So unless I say times Rn plus 1 is continuous as, okay, so I said call that, so continuous or smooth meaning infinitely differentiable. So we'll often write C infinity for this. You would have seen C1, etc., right? So once continuously differentiable is C1, twice continuously differentiable is C2, just continuous is C0, and so on. So C infinity is Ck for all k. So those we call smooth. So U, of course, is open, so I'm not going to mention that separately. So this precisely if the associated function is, so the associated map. So the associated map x from U to Rn plus 1 is continuous or smooth. And this is, of course, from calculus of several variables, you know that these things you can do component wise. So each component, so xj of this map x To this I can actually call function. Yeah? So because it's real valued u from u to r. So where j varies between 1 and n plus 1. Okay. So j varying between 1 and n plus 1 is continuous or smooth. On the other hand, there is certainly one object which you would have surely seen. So what we saw was, okay, given a smooth vector field, we have a collection of functions on u, n plus 1 functions on u. These are the components of the associated map. So on the other hand, this you have already seen, probably in the very definition of surface for u, is given a smooth function on u, you have an associated vector field called the gradient vector field, right? So given, so what we saw was given a vector field, smooth vector field on an open subset of Rn plus 1, we saw n plus 1 smooth functions on U. On the other hand, given a smooth function on U, so U is open. So I won't mention it every time, but we have an associated smooth vector field, which is called the gradient vector field. This, of course, you would have seen in the very definition of your regular surface. You have the gradient vector field. So the notation is nabla. So nabla f with an arrow on top is a vector field, right? Vector fields always have arrows on top. What is it? As any vector field. So this is a map from U to Rn plus 1 times Rn plus 1. How is it given? Defined by, so at a point, so how do you specify a vector field? Because it's a map, you say what is it is at every point. So I take an arbitrary point P. I have to say how this is defined. So I say this is the point P itself, and then all the coordinate vector fields, right? So dx1 at P, coordinate tangent vectors, dx n plus 1 at P. Where, okay, so I wrote my usual shorthand, where of course this is just notation for dxj. At P is simply notation for d by dxj at the point P. Right. So what do you mean? How? So you want to say what its action on a function is? It's just the derivative of the function with respect to the jth coordinate at the point P. Yeah. So the usual partial derivative is just df by dxj at the point P. So you can view this as an operator if you want. Yeah? So as a map, as a linear map. Okay. So I so that is okay. So it's a distinguished vector field. As you know, this you need this for the very definition of a surface. Um, so what we will spend uh, some of our time, so in fact much of our time today, will be on looking at curves inside surfaces that one wants to see. So initially, of course, just curves in Rn plus 1. So, and we will use this to study geometry. As you will see, measuring lengths or angles and so on is most helpfully done by the use of curves. So, and curves are nice objects, right? So they are maps from an interval to whatever space you're interested in. So parameterized curves. So what are these? So these are maps gamma from an interval I smooth maps. So everything will be smooth for us to Rn plus 1. So initially everything for Rn plus 1, and then we'll refine this to lie in surfaces. So smooth map. So I put C infinity. I is an open interval in R. So interval is also important. So connectedness, we will have occasion to use connectedness of intervals. Um, I mean, typically it doesn't have to be, but we will always stick to this. Yeah? So it doesn't have to be that curves are only defined on intervals. It could be on a, so, but we will stick to this. Of course, you can write out the components because it's a map from an interval in R to Rn plus 1. We write out gamma as the tuple of its components, gamma to 1 to gamma n plus 1. So where each gamma j is smooth function, real valued function on the interval that we have on which gamma is defined. So this is again for 1 less than equal to j less than equal to n plus 1. So the next notion you probably have all seen in some form or the other from physics, school, or probably vector analysis, calculus, something of this nature. This is the so-called velocity vector, right? Certainly, we have used this in physics, whether or not we gave precise meanings to these things, but we understand what this is. Why velocity? Because, so in classical physics, you think of a particle moving along a curve, right? So you look at gamma as a map from I to Rn plus 1. So how do you view this? You view this as, let's say, so suppose I is contains 0. So you could view this as the point gamma of 0, something in Rn plus 1, moving in time along the curve, right? So typically you think of classical Euclidean physics here, motion of particles along curves. So velocity comes from that. So certainly the name comes from physics, no question about it. So of a parameterized curve, at a time, let's call it t naught in I. So maybe parameterized curve gamma. Maybe it's good to write these things. Parameterized curve gamma from I to Rn plus 1, where um, at a time t naught in I. So we call the parameter in I to be the time parameter because of this thing I said, right? So as you think of particle moving along, so the motion is with time, is the vector. And the notation, I usually use gamma prime, but since he uses gamma dot, I'll stick to this. So this is simply the notation for the velocity vector at the point of the curve gamma at time t naught, and this is simply gamma t naught at that point. What is the associated tangent vector? This is d gamma by dt at the point t naught. So you could of course write this in terms of because gamma is a map from an open subset of R to Rn plus 1, you could write the component functions explicitly. So this you can write as a tuple gamma 1 at t naught to gamma n plus 1 at t naught. Maybe I don't even need the other brackets. I'll just let them be. So this is just d gamma 1 by dt t naught d gamma n plus 1 by dt. So just the derivatives of the component functions. So you get n plus 1, something n plus 1 cos n plus 1. And so again, ideally here a picture should be drawn. So let's see. Maybe I try this as well. Let's take a point here. Let this be gamma t. So gamma t, and okay. So let me draw. What is the velocity vector here? Because the derivative is tangent, right? So, so you should think of it like that. So this is gamma dot t, the vector. Okay. So and so as I said, this is just classical Euclidean motion. So think of gamma t as the position of a particle at t. So the heuristic is that gamma t is the position of a particle at t, time t, point particle, right? And gamma dot t is the velocity with which the particle is moving at the point gamma t. Yeah, so particle is moving at the point gamma t. Okay. So the important idea with which geometry will be done is from the pictures here, you already notice that there are certain patterns which arise, right? So you have these pictures for these vector fields, and you can imagine curves which fit these vectors, right? So what do I mean by that? And this idea of curves fitting these vector fields is an important one. And this really leads us to the notion of what integral curves are. Right? So all of these notions we'll again look at on the surface, but it's very helpful to do it in Euclidean space first, and then do this on the surface. So integral curves. So you are given a smooth vector field. So u2 rn plus 1 times rn plus 1 is a smooth vector field. U is open. Yeah, so this is always going to be the case unless I state otherwise. So what is an integral curve for this vector field? An integral curve gamma of the vector field x is a parametrized curve, as I said, which fits the vector field. What does it mean that it fits the vector field? It means that the velocity vector at every point on the curve actually gives the corresponding vector given by the function associated to the vector field at that point, right? So let me, so it's a parameterized curve gamma from I to Rn plus 1, sorry, I to u, so such that it fits the vector field in the following sense. You look at the velocity vector of this curve at a point t. This gives you the tangent vector corresponding to the vector field x at the point gamma t. Yeah, so this is the defining relation. For what an integral curve is. So in this sense, it fits the curve, right? So if you restrict your vector field to just points on the curve, so at every point, if the velocity vector of the curve and the vector given by the vector field, tangent vector given by the vector field actually coincide, then you call the curve an integral curve. So maybe I write this in words. That is, at each point on the curve, the velocity vector coincides with the tangent vector given at that point. So the velocity vector of the curve gamma coincides with the tangent vector given by the vector field at that point. Or the associated function, right? So given by at the point gamma t. So at that point, maybe without saying. So again, here I will. It's a nice picture given in your book. So I will simply copy that out. So this is an even harder picture to draw than the previous one. The previous one, at least, we could have drawn and agreed that what I drew was correct, was precise. Here, this is harder to do, but look at the picture closely, right? So you have a curve which is a spiral here, and the vectors of the vector field are given by these arrows. So what does it do? At every point on the curve, the velocity vector and the vector given by the vector field at that point are the same, right? So in other words, the curve fits these arrows given by the vector field, and such a curve is called an integral curve. So the fundamental notion which will be very, very useful. Yeah. Now, of course, the look at this shaded equation, the defining relation between the curve and the vector field. So if you write it out in components, what happens, right? So notice that the defining condition of gamma being integral to a vector field x to x gives rise to a system of ODEs. I just write component wise and equate to the, because we know what the velocity vector is, we know what the vector field is in terms of the in terms of the component functions on the left hand side, component functions on the right hand side, and we simply equate them coordinate wise. So system of ODEs I'll write the ODEs down and then maybe stop for I don't know how long. That we'll see. But so each component. So I look at d gamma 1 by dt at the point t, or t naught if you wish. Yeah. So this should of course go to the first component on the right hand side. What will that be? That will be x1 of recall that the x1, xn plus 1, these are the component functions of the map associated to the vector field, right? Map x associated to the vector field x with arrow on top. So this we write in terms of components as well. So just equate both those. So this is gamma n plus 1. So there's a whole system here. So until d gamma n plus 1 by dt at the point t should be the same as xn plus 1 at the point gamma 1 t, gamma n plus 1 t. So this, of course, this whole system for all time t in the interval I where gamma is defined. So that is the system of ODEs. And but you have something more. So perhaps I will specify that. Um, Often we take integral curves passing through a specific point. So, okay, so that maybe I stop with that remark. So if we consider integral curves to vector fields through a point, so maybe an integral curve gamma to a vector field through a point. So I want to, so through a point P, that is, for us, through a point would mean gamma of 0 is P. So in our definition, so I will always be an interval around 0 in practice at least. So in theory, it could be any interval, but we fix a parameterization so that the interval contains 0. So through a curve going through a point will always mean gamma of 0 is the given point. Integral curve through a point to a vector field X then we also have smooth initial conditions for the system of differential equations. So we have the following smooth initial conditions. So what are these initial conditions? Because you asked that gamma 0 is P, it means you write component wise. So gamma 1 of 0 is P1 and so on until gamma n plus 1 of 0 is Pn plus 1. So you have a system of ODEs where with smooth initial conditions. So this is just arising from the additional requirement that the integral curve passes through a given point that you are interested in. So P, of course, is a point in Rn plus 1, right? So it has n plus 1 components. And so as you may imagine, the existence and uniqueness theorem for solutions of systems of ODEs will be the fundamental idea. But I will stop here.